Hi, everybody. Today we're going to talk about central tendencies and normal distributions. So, really, the heart of statistics is based on the idea that if you take a set of data, it distributes across a curve. And sometimes it looks really nice and well distributed. And that's called a normal distribution. So what we're going to do is we're going to take a look at some normal distribution concepts today, some of the vocabulary associated with it. I'll draw a few pictures for you, and then we'll take you through two other videos. One which shows you how to hand calculate some of the rules around how data is distributed, and the second on how you can visually represent some data that is normally distributed using SPSS. So theory first on this video, how to calculate some variance factors around distribution. Second, and three, how to make a graph with our first SPSS task of the box plot. So when we examine data and their trends, we want to have knowledge of their shape. And when we say shape, it's like, how does the data distribute? So I'm going to start off by just drawing you a little section here, and I want you to consider what this looks like. So let's go to my camera. Okay, so let's take this sample data where I've got score of 5, 4, 3, 2, 1, maybe like advanced placement scores or test or something. And then N, number of individuals with the score. So one person got 5, 3 got 4, 5 got 3, and 3 got 2, and so on. So I'm going to make a little graph to display the frequency. So let's say 1, 2, 3, 4, and 5. So one person had 5. So let's put like, I'm just going to use an X to represent that. 4 people got 3. 1, 2, 3. 5 people got 5. So 3. 5 people got 3. 1, 2, 3, 4, 5. 3 people got 2. 1, 2, 3. And then one person got 1. Okay. So this has a very normal shape to it. We can tell by looking at it that the mode is 3. The median is 3. The mean is going to be 3. Everything's going to be 3 based on the even distribution of these data. But what I really want to show you with this distribution is like, there is your bell. See, there's your bell-shaped curve. So when we talk about a bell-shaped curve, it's talking about the distribution of the data points and then the even curve associated with it. So measures of central tendency are indicators of average scores. Like scores are not all the same. Individuals do different things when you're sampling data, even in experimental laboratory settings, data spreads out. And when you find patterns of normalcy, that better helps you describe and understand what you're looking at. And then when you're doing normalcy, you want to also have measures of variations. In other words, how does the score spread out? If I have a curve that looks like this, that's different than a curve that looks like this, or different than a curve that looks like this. Now, there's some important letters associated with normal curves, and so we're going to use some of the vocabulary now to review what the curves look like. So first, we see the letter X with the subscript I. It's actually the Greek letter chi, and so chi I or chi initial indicates individual data points, and this will be important when we do some hand calculations. And then we have chi with the bar over the top, sometimes referred to as chi bar. That is also the mean or the average of scores. Sometimes it's represented by the letter M or the Greek letter mu. N refers to number of terms or number of data points that exist. And SD or S is the standard deviation. And the standard deviation discusses variance from the mean. We'll talk separately about standard deviations and how to hand calculate that. And then the Qs are important too. Those are the quartiles. So in a data set, you'll have the lowest score, the minimum. You'll have the highest score, the maximum. And 50% along the way is your median. So minimum, maximum, and median. Okay. And so 50% of the data is below the median. That's that area. And then 50% of the data is above the median. Easy to understand. The Qs are the quartiles. So the Q1 is the 25th percentile. So if this is the median, this is the minimum, the Q1 is about here, or at the 25th percentile. The Q2 is actually just another term for the median, and the Q3 is the 75th percentile. So between Q2 or median and Q3, 25% of the data, and then the last 25% of the data is on top. The terms that you probably are most familiar with in terms of central tendency are, middle school math terms in some sense. The mode, the most frequent score in a distribution, the median, the 50th percentile, and the mean, the average of all scores. So the median and the mean are different, and they tell you different things. Especially if the scores are distributed. If the scores are distributed really well and really normal, and you have a beautiful bell-shaped curve, the median and the mean might be very close to each other and or the same thing. However, when data is not perfectly distributed under a bell curve, then they might be different from one another. And we can take a look at what some of that means. So here's a symmetric curve. This is like the classic bell curve. And in the classic bell curve, we have the median. So that's the middle 50%. So that means 50% of the data is on this side of the curve, and 50% of the data is on that side of the curve. Here's a bimodal distribution. It's like kind of the double hump. It's like, what is it, the camel or the dromedary? I can never remember. And there are two modes, which are rather large. Lots of data points here and lots of data points here. But the median and the median are suppressed. So they're not showing the nice symmetric curves. And then the real life situation is you often have skewed data where data is not evenly distributed on one side of the median or the other side. So here's the median. And again, 50% of the data is spread out in this short distance here, but the other 50% of the data is spread out like all the way across here. You probably recognize this best as like Amazon stars, right? The majority of people get 4 and 5 stars on things. And so the majority of the data is here, or 50% of the data is here, but you get far less that are 3, 2, 1 stars. And this is a skewed to the left. And the reason it's skewed to the left, you say, well, that's like the bump is on the right. You've got more data spread out here. So it's skewed or spread out to the left where there's less to the right of the median. And then the skew to the right is just the opposite of that. Here's another way to think about the data. So if this is a distribution of scores, each score represents a different data point. This is their post-test score. Well, here's my median right here in the middle. Here's my minimum, and here's my max on this side. So therefore, here's like the 25th percentile, and here's the 75th percentile. So minimum, Q1, median, Q3, sorry, maximum. Now we're going to move on to measurements of the variation, how they are spread out. So there will be a separate video just on calculating standard deviation and its the following concept, z-scoring. I'm going to talk about them in broad terms right now, and then we'll actually go through a calculation of standard deviation and z-scoring. I'll give you a nice example of z-score in the standard deviation and z-score video. So variance is the average of the sum squared deviations around the mean. It's a mathematical construct. It's not used very often in statistics, but the concept of variation and variance go together. One is used is the standard deviation, which is the square root of the variance expressed in the same units. And the reason we like it is it's expressed in the same units as the measurement of the variable. So it takes the the proportions of the variance. So here it is, the square root of the sum of the chi-initials minus the means squared divided by n minus 1. So we'll go through what all that means separately so you can better understand it. But really what standard deviation is it tells you how much data is spread out over the curve and where the cutoff points are. So here's a beautiful bell-shaped curve, and this is saying normal distribution in z-score, but the z-scores relate to the standard deviation very closely. I love using z-scores for calculating things because it gives relationships really well and it standardizes all data. Here, the z-score is equal to 0. It's the mean right here. And then a certain distance away, you get a z-score of 1 or a z-score of -1, which means standard deviation, the mean plus the standard deviation, one standard deviation this way, and the mean minus one standard deviation this way. Now, you see all these funky numbers here. 34%, 0.34 or 34% of the data is here. 34 is here. So 68% of the data lies from the distance of the z-score of -1 or one standard deviation less than the mean through the z-score of +1 or one standard deviation plus the mean. So the majority of the data is here. And then we move out and we get two standard deviations, -2 and +2. And this distance here is 95% of all the data fits into the first two standard deviations or z-scores of -2 to +2. And finally, 99% of the data, so very little, like 95 to 99, it's like 4%. Like 2% of the data is here, and 2% of the data is here. And then less than 1% is outside of the third standard deviation. So you'll check out the standard deviation and z-score to better understand how those are hand calculated and what they really mean when you hand calculate them. And this is just the formula for calculating z-scores, and again, a really useful calculation in statistics. After you have a chance to look at standard deviation and z-scores, we're going to also take a look at box plots. I love the box plot. It is my favorite visual representation of data in graphical format. And the box plot showcases the measures of central tendency. And it starts with the median and it shows the dispersion in the boxes. So the things I was talking about before when I was doing these drawings, the minimum, the median, and the maximum, and then the interquartile range, which I will show you visually what that looks like. So this is a box plot. It's sometimes called a box and whisker plot. The reason it's a box and whisker plot is here's the box, and then this is the whisker. It's kind of like a cat whisker, I guess, is the idea. But you have the minimum. The minimum is marked by the little hash. Then you have a line, which takes us to the first quartile. That's the 25th percentile. So in this example here, 25% of the data is here. And then we have the box, which is the interquartile range from the 25th to the 75th percentile. So here's 25 to 50, and here's 50 to 75. So 50% of the data is in this range right here, 25% in this range, 50 in this range. And the last one, this has got a little skew to it, if you take a look at it, is up here. This one is skewed right. If you turn your whole screen sideways, you can see why it's skewed right. Here's the 75th to the max, or the 100th percentile, and that's 25% of the data. So this data is much more spread out in this example. Now, when you calculate and produce box plots in SPSS, you have to take into you don't have to take into consideration. The computer takes into consideration outliers, and outliers are unusual scores, usually at the extreme ends. So SPSS doesn't make a pure box plot with the minimum and the maximum. It actually does a modified box plot, and it uses the interquartile range, and it sets a reasonable upper and lower bound limit. And that is mathematically defined as 1.5 times the interquartile range. So instead of saying the max, so if this is the median, and then the 1.5 of the interquartile range plus the Q3 will get you maybe to here instead of here. Right? Alexander there. Get you to here instead of maybe here. And that way, if you do have data points that are outside of 1.5 times the interquartile range, you can identify outliers. In SPSS, it'll put a little star next to it, or a star right on the data. Sometimes it puts a little circle, and we'll see some examples of that in the box plot video for you. So here's how I kind of like to put it all together and see it together. This one is actually using the modified box plot method. So here's the box plot, and this is a really well normally distributed situation. Here's the Q1 and the Q3, and that's the interquartile range, and that's the middle 50% of the bell curve. Here is the upper bounds to the maximum, and here's the lower bounds to the minimum. And if you notice, it doesn't add up to 100%, right? The reason it doesn't add up to 100% is because there's some little bit outliers right outside of here, which is, when we talked about it, the outside almost of the third standard deviation. Not quite, though. This graph does put it on the standard deviation plots, 1 standard deviation, 2 standard deviations, 3 standard deviations out here. So here's the 68% and then the 15% on either side of that, the other 30%. So you can see the standard deviation is a little bit wider than the interquartile range. So here's the middle 50% in the interquartile range. So like the first standard deviation is like from about here to about here. There are other ways people sometimes represent data. They use normal curve equivalence score, so it puts it on a normal curve. And it's a mathematical calculation. You can do percentiles or Stanines. These are some other methods for using data and representing it in a different scale other than z-scores. So if you're interested in those, we're not going to actually use them directly in the course, but I do want to expose you to the terminology. So next steps. Look at the standard deviation and z-score. Watch me hand calculate some of that for you. We'll go back and forth between the computer and the screen. And then also, second, watch the box plot, and you'll need SPSS for that. That'll be our first SPSS task, to create a box plot using SPSS. All right, let's see in a few.